spent most of my time in industrial research labs, but I was at 2 startups, this being the second one. And you can find out more if you want about me, but this is not about me. It's about streaming systems. And of course, it's a streaming systems conference. And today, I think I'm going to give you a glimpse into the future. So I've been often wrong, but I think I'm right on this one. I'm going to make some predictions. So today, database and streaming systems are different. They are different systems built by different companies. They work in different ways. I actually claim that this is not necessary. And I think the next decade will show that this can be unified in a single system that does the job of both better than either of those two does it today. And I think databases and streams are just facets of a same object. And one thing that unifies them is the incremental view maintenance problem. Don't worry about it if you don't know what it is. Hopefully, you'll know by the end of this presentation. So the subject of this talk actually has been published in some academic papers. And the papers got some awards. If you really want to know how it works, you're welcome to study those. And it's also open source. Everything I'm telling you, you can download yourself and try if you want. OK, so what do you mean by no compromise? So if you look, both database and streaming systems, they make compromises if they want to work in a regime designed for the other side. But I think this is not necessary. What we can do is we can run any kind of SQL queries with no restrictions, including recursive queries on tables and streams. We can analyze data from any mix of data sources. They could be what people call tables and streams, but they can be files, they can be events. It's not necessary to even separate those two as different concepts. And I think we can handle any kinds of changes to the data. We can support insertions, deletions, or updates. If you look, many streaming systems are designed for insertions, but you can generalize this and work with any kind of data changes. And moreover, we can evaluate these queries incrementally, which means that when you compute the result of these queries, you can do it doing work proportional to the size of the change. And this is very important, especially in systems that have very large data sets or accumulate streams over long periods of time. And this is the technology called incremental view maintenance, which I'm going to talk more about. And you can do all this without sacrificing the semantics of your programs. So you can run computations on streams and get exactly the same results that the database would have given you if you had accumulated all the data on these streams. So, and you can get strong consistency, transactional semantics, and fully deterministic execution even on streams. And then all of these can be achieved without heroic efforts. So actually, what is amazing is these problems, people have been working on them for at least 40 years. It turns out that the solutions are quite simple. They use a uniform data representation. And this same representation of data can be applied to the changes that you apply to the data. And I'm going to tell you how it works. And then you can also use this to compute on unbounded data sources like streams that people call event streams, even when your computational resources are bounded. Not any queries, but you can do amazingly well. OK. So by the way, as I said, and as our host has said, if you have any questions, I'll be very happy to take them. Just raise your hand, and we'll clarify. So the setup is this. We assume you have a database, the cylinder at the bottom, and on the database, you run a query. The query gives you a result, some table. This is where we start from. Then the database changes. That's what databases do, right? You keep adding, deleting stuff to the database. The database tends to be large. You could say, let's say 1 billion rows. Doesn't matter. It's a large number. The changes tend to be smaller, right? Whenever you change, you insert a row, you delete 10 rows. So these are much smaller. And then I'm showing time going to the right, this blue arrow. And the database keeps changing. So you make some changes, you get a new version of the database, and so on. These changes, database people, they call them transactions. That's how database advance. A change is not necessarily one row. You could say, I want to change these 10 rows. I insert 10 rows in a table. I delete 10 rows from another table. And I want to do this atomically. I want this to happen as if it happens instantly. OK. Now, the setup that we're interested in is the so-called periodic query evaluation. You have a query, and you want to run this query over and over. You want to know the query at the beginning, then you want to know what the result of the query is after you have inserted some rows, deleted some rows, and so on. So you want to evaluate this query for every version of your database. That's what we're interested in. And this is actually done by databases today very well using views. So you say create view, and then you specify a query as select, using SQL. This view is actually what is being maintained by the database, by the query. It's reevaluating the query every time the database changes. The view is supposed to change as well. Okay, so this V is the view that you get. You get a different version of the view for every version of the database. Okay, so what is incremental view maintenance? So you can certainly do it this way. Every time your database changes, you run the query again. But remember, the database is large. So these green arrows, they could be very expensive. They have to look at everything in the database. What if, instead of computing the new versions of the view, we could compute what changed in the view? Maybe these changes are also small. In many practical cases, they are very small as well. So what we want is a blue query. The green query was looking at the whole database, but the green query only looks at the changes. And since the changes are much smaller than the database, maybe we have hope to do this much, much faster. And this is what people call incremental view maintenance. These deltas, delta is usually the sign of a change or an increment. So deltas are the increments. And what we want is to compute directly on the increments, on the changes. And this is very valuable if you can do the work as time proportional to the change and not to the database. Okay, so this is what we want to solve. I'm going to use some diagrams. If you know how queries are evaluated in database systems or in streaming systems, they usually have a set of operators and the data flows between operators on edges. So I'm going to use this representation for query plans. People call them query plans. Okay, so this query queue happens to be implemented by some operators. You don't need to know what the Greek letters mean. It doesn't matter for this talk. Okay, the second concept that I'm going to make precise is the stream. So a stream is just a sequence of values. So it's a very, very simple concept. So the stream, you could say if you read from right to left is 1, 2, 1, 0, minus 1, minus 2, minus 1. It's just a sequence of values. The values can be anything. And now, what streaming systems do, this is a streaming systems conference, they compute on streams. So you build these engines, and the inputs are not one value. Each input is a sequence of values, and the outputs are also sequences of values. Okay, so this is a stream computation. And I'm going to show when the data values are streams, I'm going to show them as double arrows. So if you look at the previous picture, here we have simple arrows because you feed one input, you get one output. But here you have a double arrow because you feed a sequence of inputs and you get a sequence of outputs. Okay, so these are streams. Now let me show you some streams that you may have never thought about. So as I said, the stream was a sequence of values. So the database itself is a stream. Okay, so it's a stream of database snapshots. After each transaction, you have another version of the database, and these form a stream. In the previous picture, we also had these changes that you apply to the database. These are the transactions. These also form a stream. This is a stream of database changes or transactions. There's another stream, which is the stream of views. If you remember, we had a view that we were maintaining. For each version of the database, we have a version of the view. This is also a stream. People don't think of databases and views as streams, but if you think about them as streams, everything becomes much, much easier. And finally, the view changes themselves are a stream. Okay? So why is this point of view useful? So first of all, this is the core idea number one, which makes your life much simpler and which will really solve this problem that people have been working on for 40 years. Everything is a stream. Databases are streams, transactions are streams, views are streams, and view changes are streams. Everything is a stream. All right. Now, a view, computing a view is a stream computation, right? So remember we had this query we started from. The query is the green arrow that computes some result on a database. You could implement this using a query plan, which takes the database and gives you the view, right? So this is the difference between the query as an abstract language object and the implementation as a plan. And if you take this query plan and make the arrows double, now it becomes a streaming computation. You feed database snapshots, and the query plan computes view snapshots out of it. This query plan is very similar to the original plan, but this is how you can build streaming computation. This is not an efficient streaming computation, but it is a streaming computation. Okay, now the second core idea is how do you represent changes to a database? So a database, you have the database and you usually say insert or delete. So the database is composed of tables. When you insert rows in tables, you delete rows from tables. So on the left, I'm showing you a table, and then I'm having a change. This delta arrows are always changes. And this change, so let's say, inserts a row at the bottom and deletes the top row. Okay? So we can read this as a mathematical operation, which deletes the top row. So it says -1, subtract the first row from the table, and then add the bottom row to the table. Okay? So this is an empty table, so the middle rows are unaffected. Think of them as shadows. And then this yellow arrow is now delete the top and insert the bottom. Okay? And now we can read the top image of the figure as mathematical addition. So we have the original table, and then we add this change, right? And then we get a new table. So this is the same as a bank, which says debits are positive, credits are negative, and then you always add something to the bank account. That what the number you add can be positive or negative. This works very well for tables. Okay? So we call these Z sets. So they are sets because they have a set of rows, and the Z comes from the integer numbers. Each row has a number which tells you how many times that row is being added or removed from a table. And this is just Z set addition. And the way you add Z sets, essentially you find the rows, and then you add people call them weights. Okay. So one other thing which is very interesting, you can think of a table in a database as a Z set itself. Is the Z set obtaining by starting from an empty table and adding all the rows of the table. Okay, so not only, what I want to say is, not only are the changes to the table Z sets, the tables themselves are Z sets. So this is a very, very powerful idea. In a database, everything is a Z set. And Z sets are much better than tables because they can represent both tables and changes to the tables, the same mathematical object and the same logical object. And in an implementation, you could have the same abstract class, for example, that would implement both. And these Z sets can be positive or negative. They can add or remove things. And they can also represent databases. SQL works on multi-sets. You can have duplicate rows. These Z sets work fine. You just have a weight of 2 or 3 or 6. You have 6 copies of a row, you put a weight of 6 on that row. So Z sets are really, really nice. And in fact, Z sets are everywhere. Let's look again at this picture. If you remember, we started from a database that keeps changing, and for each database version, we compute a view. I'll point you some Z sets on this picture. The database itself is a collection of tables. Tables can be represented as Z sets. The views are tables. They can also be represented as Z sets. The changes to the views and to the tables are also Z sets. Then people talk about change data capture. Change data capture tells you what changed in an external database. These are also Z sets. Database logs. Database logs tell you what changed in a database. These are also Z sets. And insert and delete statements. What are insert and delete statements? They just describe how you change a table. These are also Z sets. So all of these can be represented with the same data structure, which is very, very simple. Each row is mapped to a number, an integer number. Transactions. A transaction tells you how you change many tables. A transaction can be represented as a Z set as well. So, and I claim that in the future, all these stupid things that people do, you have to go to great lengths to extract data from a database or to send data to another database, serialize it in various formats, do all sorts of conversions. This is totally needless. You should use Z sets as a standard representation format and exchange data between databases with much ease. Okay, so remember we have a database and we change it by applying delta to it. As I said, this is the same thing as adding in Z sets. So now, if you have a database and you apply one change after another, this means, you say, add a change, and I add another change, and so on. So you add many changes, you get the nth version of the database is just adding the changes, all the changes you've seen so far. And people will call this integration. This sounds very scary, maybe, but I actually will assure you that it's not scary. This is, in fact, how each of you works. You are a database, and you get a stream of information from your sensors, from your eyes, from your ears, and people say you are the sum of your experiences. That's exactly what it means. You listen to me now. I'm telling you something, and my words come to you one by one, and you integrate them in your mind. You add the information layer by layer. You accumulate what I tell you, and then this is how you build an understanding of what I'm trying to convey to you. This is how all organisms work. We are just integrators. So this is the stream of experiences, and your brain does keep adding to your database of knowledge the information that you get from the outside. You also forget. Sometimes you subtract from the database, but it's also an operation of addition. And forgetting is very important. But we're not talking about that. Okay, so let's come back to the problem we started from. We have a database, and we want to maintain a view incrementally. Right? So we have this green query, and we want to compute it over and over. Ideally, what we want to do is to compute directly the changes to the view when the database changes. And indeed, what we can do is the following. And this is what we have achieved. This is what this work is about. Let's say you have a query, and you know how to execute the query on the database. So this is what databases do, right? You type queries, they generate plans, and then they run the plans. What we have is a compiler which takes this plan and generates this Q delta, the blue one. It generates it for you automatically from the plan of Q. This Q delta is now a different kind of object. It operates on streams. The inputs are streams. You feed to Q delta all the changes to the database, and it gives you all the changes to the view, one by one. As you feed one change to the database, it gives you the first change to the view. It gives you the second one, it gives you the second change to the view, and so on. This is completely automatic and very, very simple. So we can do this for any query. Nobody could do this until they could do it for some kinds of queries. Now we can do it for any kind of query. So one point I want to make is that Q and Q delta are a little different, because Q looks at the data, generates the output, and that's it. It forgets everything. Whereas Q delta can accumulate information in its internal brain. So it's actually a stateful system. It has information. Every time it sees a new change, it will accumulate some information and then generate the next change. So the incremental version of a query is not a query. It's a streaming system. So that's why it's very, very useful to think of everything as being a streaming system, including your database. So this streaming system is, mathematically speaking, it runs forever. So every time, and like humans, until we die, we run forever. We keep accumulating changes that we see in the environment. And we have eternal state. Humans have memories. That's what makes us human. Okay, and I promised you we can do any query. That sounds kind of excessive. Queries can be very complicated. It turns out there is a property which is amazing. Every time I think about this, I'm still shocked that it's true. If your query is the composition of two simple queries, right? And if you know query languages, they are based on something called relational algebra, which says that all queries are expressed in selection, projections, join, filtering, and stuff like that. Just a small number of operations. So any query is in the end looks like that. It's a composition of simpler queries. What our compiler does, actually, our result is that if your query is a composition of two simple queries, you can just compute the incremental version of these simple queries, and you get the total blue arrow. So it just says, if you have a plan for the query, I just take the plan, I take each primitive, I incrementalize it, and I get the incremental computation for the whole query. It's a really surprising result. So if you go back to the relational algebra, if you know how to make incremental selection, projection, join, filtering, and aggregates, you're finished. You can do all of SQL. Because any query in SQL is a composition of these. And it works. So essentially, if you know what your primitive operations are, and you know how to incrementalize them, you just put them together, and you get the incremental version of a query, for an arbitrary query. So that's why you have no compromises, because you can take any SQL query that we know how to execute, and we convert this. We have this algorithm which will convert it into an incremental query. We can operate on any mix of data sources, because this algorithm works for any query that operates on streams or tables. Streams and tables are the same things. They are Z-sets. And we support any changes to the tables, insertions, updates, or deletes. Insertions are just Z-sets that add +1, deletes are -1, and updates have a -1 and the +1 with new and the old information. So the Z-set is this miraculous ingredient which allows this to work. And then all this is incrementally evaluated. So each primitive does work proportional to the size of the input change that comes to it. So Q delta, this query that I promised you that will only look at changes, we know how to build this, and this is an efficient query. And we get the exact semantics of the SQL program that we started with. You don't have to worry, So if you look, let's say a system like Flink, has this notion of event. Event has a timestamp, and then there's some watermark. Has all sorts of very complicated things you have to understand to see how the system works. You don't have to know any of that. If you understand how the database works, then the streaming system works exactly in the same way. You don't need to add additional properties or features to it. That's very nice. Essentially, this Q delta is supposed to do the same thing, but piece by piece instead of all of once. But otherwise, the result produced should be exactly the same. And as I said, we have a simple representation for data and for the algorithms. The data is always a Z-set. Everything computes on Z-sets, and the algorithms look a lot like the algorithms that people use in databases. And this I haven't covered in this talk, how you do computations on infinite data. But that's also a nice feature. So look, we get everything a database can do, and now we can run it on streams. That's why this is there's no compromise. But also we get the opposite. Everything a streaming system can do today, now we can integrate in a database. And I claim that in 10 years, all the databases will be doing this, or they will be obsolete. All right? There will be no more database and streaming systems. There will be unified systems that do both. I'm willing to take a wager, if anybody is up to. OK, so if it's so easy, how come nobody's done it? I mean, maybe I'm just lying. It's a possibility, That's how many charlatans make a living. And I'll give you an explanation. So these are actually three simple ingredients, streams, changes, Z-sets, and queries. People have known about this stuff for a long time, but they haven't put them together. Turns out that the way today's databases are built, they don't understand negative changes. People always think about what is the value of this table, but they don't know how to remove stuff from a table. For that, they can recompute it from scratch. So it's very hard to take something like Postgres or Snowflake and retrofit this algorithm in them. That's why they haven't done it. But they will do it. I guarantee you. Once they understand how powerful this will happen instantly. So people have done this for some restricted forms of these algorithms. And you can, Flink is all about incremental view maintenance. It's all about appending to a stream and computing the changes to the output. That's what it does. But it only does appends. It doesn't do deletes. And if you look Snowflakes and Materialize and lots of other systems, they can handle some queries or some updates. I say that's not necessary. You can handle any queries and any updates. I had prepared a demo for you. Do you have any questions? I can show you how the system looks. Query? Question? No? So I was supposed to have a co-speaker, but he couldn't travel, so he instead recorded for me a demo. I would have liked to give it live, but yesterday I went to several talks and I saw demo failures, so I got scared, so I decided to have a video instead. So this is a screenshot of, let me start it, of our UI. The UI is not interesting, but what you do, you type SQL. So you create tables, but the tables are not real tables. They are just facades that talk to the outside world. And you specify a table can be a Kafka stream, or it can be a real table, or a CSV file, or some event stream. And you can have any number of tables of any kinds. And they can have arbitrary schemas. They can have any number of timestamp columns. Anything you can write in SQL, you are allowed to do this. This is modeled after fraud detection application where you have customers and the customers do credit card transactions. So let me pause this because I'm not keeping his pace. So we have two tables, people and what they bought. And each person has a state of residence, and each purchase has a state where it happened. So now we want to find the purchases made out of state, because maybe somebody steals your credit card, they want to go out of state and then splurge. So we can define a view like the top one, and we just look at the transaction. So first of all, we need to join the two tables, right? When somebody does the transaction, we have to find whose user the transaction belongs, and then to see if they are from the same state. So we enrich, this is called enrichment. We enrich the transaction. For each transaction, we remember whether it's in state or out of state, and for this, we have to combine data from two sources. And then we also, sometimes you travel. And usually when you travel, you're not going to make one transaction. You're going to make a bunch of transactions. So we want to see transactions are suspicious if in the last 30 days, let's say, you have done few transactions out of state. But if you've done many, maybe then it's OK because you're traveling. So we can define window type queries which say, how many, look at all the transactions over the 30 days and see how many are out of state. So that's another kind of enrichment. And then we declare some transactions suspicious, red, if they're out of state and there's not too many nearby transactions, and we declare them fine otherwise. So there are two views which are declared this way. And notice that some views depend on other views. So you build a view from the first two table, and then you build the anomalous transactions from the other view. Views are free. You can define as many as you want. In other database systems, that's not true. Oh, this is still running. It's now I'm ahead of the video. Okay, so eventually we'll move up. Another thing I want to point out, this join that we did. So here is essentially for each customer, we'll have the total amount of their purchases and how many are red and how many are green. And then we used a special kind of an as-of join. I'll explain in a second why we do that. That's because people can move. So a person actually can have multiple addresses, and when you check, you should check the current address at the time they made the purchase. You'll see why this is important. So that's another thing. That's an operation you can do. These are relatively sophisticated operations. And now we started running. This actually is fed by a random data generator, which generates random transactions. This shows you, the throughput. It's supposed to generate 1,000 transactions per second. We can do much more, but what I'm going to show you is several interesting features. So what we want to see, this is a view which shows you how the changes keep coming. There's 1,000 per second. You can't see all of them, but the point is that they come to one of the views that we compute. So remember, we only compute what changed in the views. So now we defined, so remember, every person has red and green transactions. These two, when you sum them up, they should total the number of, the correct amount they spent. Something is either green or red. It can't be anything else in this model. So now we have a way to inspect these views that keep changing, using a command line. And I'm going to run a few, my coworker has run a few commands and recorded them. So now the first thing he does, he inserts a new customer that we know for sure wasn't generated randomly. So this is Jane Doe in California, all right? So now we'll make this customer have two transactions in New Jersey. So the customer spent in New Jersey, had two transactions. These are supposed to be red according to our rule. So now let's see what are the red transactions for this customer. So we are looking at the view. Indeed, they are red. So we looked at the red transactions table, and these two are suspicious because there were two transactions out of state. Now, I'm a Bank of America, and I inquire about this, and I find out that the customer actually moved to New Jersey. So then I have to update my database. So I say, oh, Jane Doe doesn't live in California anymore. She lives in New Jersey. So now, are the transactions still suspicious? Let's see. Are they still red? No, they have vanished. The view has been automatically updated to reflect the past knowledge, okay? So the bank didn't find out, the customer didn't inform them, but when they found out, this as of join compared the date of the transactions with the date of the move when we found out the customer moved and declared the transactions are no longer suspicious. And as I said, we also have this final view, which is a kind of a consistency check. It says any transaction should be either red or green. So now maybe this looks trivial, but I guarantee you many streaming systems today, they don't have this notion of internal consistency. So if you look at their transactions, you'll find that some transactions might be neither red nor green. Frankly, I think if you're a bank and you use such a system, you should throw it away. Maybe it's good for some other applications, but this model of streaming that I'm explaining to you is guaranteed to always have this model of consistency because we evaluate all the views on the same snapshot of the database. There is a notion of the database version, and now what we do here is actually we run this, we look at the views, we look at the transactions, and we have a green amount, a red amount, and the total amount. No matter how time we evaluate this query, the green and the red added together should equal the total. Well, try to do this experiment on other streaming systems. I guarantee you that none of them, maybe except Materialize, will have this property. So it looks difficult. It's not difficult. I think this should be what we start with. No compromise, all right? We don't want to compromise on the quality of the results just because the system is a streaming system. And we can do that. So that's my message. So what did we do? Let me go back to presentation mode. So we wrote a compiler. The compiler takes an arbitrary query plan as input, and it generates an output which is an 100% equivalent incremental query plan. This incremental query plan will look at what's new and will tell you what's new. And this system can operate on any combination of streams and tables, any number, and can compute any number of views concurrently with very strong consistency promises. And it can handle any kind of changes, insertions, deletes, or updates, and any kind of things you can write in SQL. You know, some systems can't handle distinct, some systems can't handle except, some systems can't handle some window queries. Well, you know, modular bugs, you know, we're a small team, so if something doesn't work, it's a bug. It's not because we can't do it, we haven't done it yet, okay? So, and I think you should request the same from your, if you want to use a streaming system or database, you should request the same thing, no compromises. You don't compromise on the quality of the results that you produce just because your system is optimized for a particular application domain. And we achieve this using 3 core ideas, which are very, very simple. I have essentially explained these ideas in full to you in 33 minutes. First idea is everything is a stream. A database is a stream. It's not just the changes that come to you. The database is a stream because it's a sequence of databases. And if you think about this way, you are a stream. You are a sequence of personalities, as you evolve through life. At each age, you are a different person. Time isn't discrete for humans, but maybe every morning you wake up, you can see another transaction has been performed. The second important idea is that changes and data are the same thing. You don't have to think of them as different, because if you think of them as different, things get very messy. But they are all z-sets. They are just, each row has a weight, which is positive or negative. And then everything the database does is just keep adding those changes. That's integration. And then the third idea is that incremental view maintenance should be seen as the process of asking what's new in the input data and then telling whoever cares what's new in the output data. That's it. That's incremental view maintenance. And we know how to do it if we rely on these ingredients.